Hello, my name is Ojas Chaudhary and I've worked on Design Assignment 1 and I worked with the group members whose names are here on the slide. This is a photo of our group. So our problem statement is a two-stage rocket is to be launched with 200 kilogram payload and the goal is to achieve maximum kinetic energy for the payload after both stages have been jettisoned. Rocket will be launched straight up from the equator, disregarding the launch angle variation, wind, and the rotation of the Earth. The mass of fuel stored in both stages' fuel tanks will be varied to achieve the maximum possible kinetic energy for the payload when it leaves the Earth. So we have to find the maximum fuel for this, keeping it under $3 million budget. I primarily focused on writing the report, validating the FlexPD model with my group members. I also attempted to write the Python script, but wasn't able to completely finish writing my own script. However, I helped in helping my group members understand the code. So for the analysis, the rocket has three forces acting on it: drag force, gravitational force, and thrust force. So we break it down these forces to start to put all the equations together. Then we also need to know the initial mass to be able to calculate the mass of the body at any time of the motion, which can be done simply by adding all of these masses here as shown. Due to the scale of this motion, distance between the radius and Earth, it is also shown to also take into account the curvature of Earth, which can then be used to find the height which will be required in the drag force calculation due to the roll changing. Then we define different times at which these stages detach. Since they detach instantaneously after the depletion of their fuel, this is then shown in terms of mass to solve for being 200 when the time have passed. From this, we can then show the kinetic energy. For the flex code, we all attempted the flex code on our own and we compared our results. So initially, this was my code and this was the graph I was getting. When reading the problem statement, I misunderstood that only stage 1 will be detached. Therefore, it yielded a slightly different value, which still had a significant difference as seen here. Although my code was not really used for the final code, but there was a lot of similarities as I've used the same method to solve. So in the final code, we can see that the beginning we define all the constants and equations given in the problem statement for ideal gas law and dry mass for different stages. Then we added our equations that we calculated in the analysis to help us model the kinetic energy using the highlighted equations here. And when running the script, we get this as the output. So we clearly see that initially the body is increasing its kinetic energy rapidly as it uses its fuel and reduces its mass from the fuel consumption. Then we see significant sudden drop, which is where the stage 1 has been detached around 16 seconds, and then we see the kinetic energy rising again much slowly this time because there's less fuel compared to the first stage. Now to see the optimization, we modified the existing code slightly as seen here in the images. We use the print only format line to export the graphs and save it as text, and then we also changed the input of the fuel mass to its highlighted in blue image. Over here we inputting values to the script with the string format method, and the numbers in the brackets show the index. For the code, it is split into 3 main sections to make it reusable for upcoming design problems. The first one, constants, where we held all the global constants FlexPD code here, and the problem also held our cost calculations here in the list. The next code is the auto sweep. This is all the necessary functions to be able to sweep through the flex file data, organize results, and run the files. In the final part of the process, linear interpolation was initially used to record data when the stage detached, but it was found to be ineffective. Instead, we used sweep range was used to multiple FlexPD scripts were run simultaneously with the help of threading module. Final data point in the kinetic energy column was used if the final pressure was 0 and final time was past the time of stage 2 detachment. These data points were then plotted as scatter plot and the curve of best fit, and the maximum and 0 points were found in subsequent iterations. So in this slide, we see our first point output that shows the fuel required in the stage 1, stage 2, and kinetic energy on the slide. Again, no linear interpolation was used. The optimization process involves zeroing in maximum 5 points from the previous run and using them as a new range of masses to plot more points and improve the data resolutions in the area. This process was repeated until the range spanned only 2,000 kilograms. Using the same method, we then zeroed in to more accurate result, which gave us second graph, which shown the max fuel in stage 1, stage 2, and kinetic energy. In the final iteration, the method used also produced the final graph. However, due to the high amount of floating point error, it became more difficult to plot the line of best fit. To improve accuracy, point count was reduced to 10 instead of 20. Instead of using interpolation, curve fitting was used by fitting polynomial into unaltered data. The first derivative test was used to find the maximum and minimum on this polynomial. So in conclusion, the requirement for fuel mass of stage 1 is 30,996 kilograms, and stage 2 is 5,120 kilograms, giving us the kinetic energy output of 12.27 gigajoules. Thank you.